last class, well, in the previous classes, in the early classes, we had shown how to start doing control problems, where unlike in your other classes that were in imaginary steady state land, this class we took one giant step towards the real world, where we don't presume steady state, we have to show that there's a steady state and that you reach a steady state. That is, before you get to a steady state, the system is unstable, and there are no guarantees that you're going to get to a steady state. And that's one of the lessons of this class, is that how do we know if you're going to get to a steady state? So that means that we have to start with dynamic models, models that have the DDT in it, you know, that term that in every other class you throw out. Sometimes it's justified, sometimes not. And we started looking at problems with keeping the DDT. And we started with linear problems, and we saw that the methods of ordinary differential equations that you had in that class, you know, your second favorite class before this one, were very useful in those problems. But sometimes the algebra could get quite cumbersome. So what we noted was that there might be another way to do the same thing, where the algebra might be a little more straightforward. And that what we saw was that we introduced Laplace transforms in order to show that. So and what made Laplace transform really easier in terms of algebra was this particular relationship. That is, if we take the Laplace transform of the derivative of a function, the derivative disappears, and we just get s times the Laplace transform of the function f itself minus the initial condition. And the nice thing is when we use prime variables, that is a variable minus its value at at the beginning, so t is equal to t1, if we start at t1, t is equal to 0 at 0, then by definition the initial condition is 0, because I'm subtracting it off, so I don't even have to worry about this particular term. So derivatives disappear, and differential equations turn to algebraic equations. Also, integrals disappear. We also showed that the integral of f of t prime dt prime from 0 to t, Laplace transform, was f tilde of s over s. So we saw that both integrals and derivatives disappeared. So we go back, all we really need to do is go back to high school, which everyone loves when I say that, because it's just algebraic equations. And presumably algebraic equations is something that makes you feel at home. Something that you know how to do and you don't get nervous about. So we started doing some illustrations to show how easy that was. And we also, by the way, we also noted that there'll be a lot more, sort of, you know, spoiler alert, there are going to be a lot more great things about Laplace transforms. Because as we will see, that, well, let me back up a second. When you transform an equation from a differential or an integral equation to an algebraic one, you solve for f tilde of s, and then but you really care about f of t. So to go back to f of t, there's some complicated complex variables math to do, but people have done that for you for many, many cases, and we have these tables. So at least in this class, we're not going to be doing the calculation. Whenever we have anything, an answer for f tilde of s, we'll just use the table to go back to f of t. So that makes it really easy. So that will give us the full-time solution. But many times we're interested in things like, is there a steady state? What is the steady state? Things like, is it stable? And as we're going to see over the course of this and future classes, you can answer those questions very often without even inverting the Laplace transform. You can just directly from f tilde of s, you can do it. We had a hint about how to do some of that at the end of the last hour. So, are there any questions on that? Okay, so if you remember, we did a problem at the end of the last hour. We did a case of two CSTRs in series, where, of course, I have CA in, CA1, and CA2. And we had a first order reaction, linear. We also spoke about previously what happens when you have nonlinear processes that a linear runs them. And we wrote out the equation for the first reactor and the second reactor. So these are the simple equations. Now the first reactor has Ca in coming in and Ca1 coming out. Ca in, we presumed, had a step change at t is equal to 0. So where this difference is Ca in prime, because it's the new value minus the old value. Now, Ca1, of course, doesn't react like that. We know that Ca1 looks like 1 minus an exponential. So we know that Ca1 is not a step change. But we have the step change coming in and Ca1 coming out. For the second reactor, instead of Ca in coming in, we have Ca1 coming in. So we have something that's not a step change coming in and Ca2 coming out. And what we did is we Laplace transformed the equations. And here I wrote out the Laplace transform of the first equation. And here I wrote out the Laplace transform of the second equation. And then here we looked up the solutions in the table. But I want to point out a couple of things here. Notice before we inverted, we noted that what we had on the right was Ca in prime over S. This is because of the Laplace transform of the step function. But over here we had Kp1, where Kp1 was T1 over tau 1, right? And that was 1 over 1 plus K tau 1. And this was the steady state gain, meaning if and when I reach steady state, this is the steady state gain. It's directly in equations. Similarly, in the second case, this is Kp2, which was 1 over 1 plus K tau, T1, tau 1, K tau 1, 1 over 1 plus K tau 2. So again, and you see it right here. So again, what you have is Ca in prime over S times the steady state gain on the right. And what do you have on the left? On the left, here I had a linear polynomial. Here I had a quadratic polynomial. Well, why do I have a linear polynomial here? Because I only have, every time I take a derivative, that turns into an S. So I only have one derivative here, so I only have the power of S to the first. On the other hand, over here, I have a quadratic equation, and that's because I had one derivative for Ca1 and another derivative for Ca2. So that's what gave me a quadratic equation. And moreover, if you notice, this particular term, where did these terms come from? The ST1 times Ca1 prime. That came from the derivative, because the derivative gave me S times something. And the 1 came from the fact that I had this on the other side of the equation. Actually, I left out a K Ca1 prime here and a K Ca2 prime. That's why it's a good idea not to take the pictures until I fix the equation, because I have a rate constant there. So where did this come from? Well, when I bring the K to the other side of the equation, that went into the T1. And the 1 plus ST1 went from this thing goes on the other side and the K goes on the other side. Both those guys go on the other side. This term and this term both go into T1. And the derivative gives me the S. So if you like, and what's forcing the system? What's causing the system to change? What's causing the system to be perturbed from its initial condition is the fact that I took a step change on Ca in prime, Ca in. So notice the only thing left on the right side of the equation is the Ca in prime. Ca in prime is on the right, and everything else went to the left side of the equation. Similarly here, the Ca in prime was on the right, and everything else went to the left side of the equation. So what is that telling us? That's telling us that the right side of the equation is the forcing. This is the thing that's causing everything to change. This is the thing that's causing things to change, the Ca in prime. The change in Ca in is causing Ca1 to change, and it's causing Ca2 to change. It's the source of all our troubles. And that's called the forcing function. The forcing is on the right. And everything on the left is the system itself, how it reacts to that change. So that's why the thing that's multiplying Ca prime tilde on the left is called the characteristic polynomial. Now, I don't care if you remember the name characteristic polynomial, But the point I'm trying to get across here is not just to do math, but to also give you an understanding of what's going on. And the characteristic polynomial is the system. It's the system itself, irrespective of it doesn't have the forcing in it. It tells you the information of how the system itself will react to any forcing. Any forcing will be on the right, but you'll always have this on the left. That's why it's characteristic of the system. And notice, since this is a quadratic, that says it came from two first-order equations, but it could have come from one second-order equation. How's that? So, first with the characteristic polynomial versus the forcing function. Someone put staples in this board, which is really dumb. Makes it hard to write. So, again, I want to make that distinction. We've got the characteristic polynomial versus the forcing function. Characteristic polynomial versus the forcing function. I haven't even looked at the solution yet. Okay, then the next thing I want to note, again, as I said, is this is obviously a first-order equation, so it only gives me a characteristic polynomial that's linear in S. I claim that this is quadratic because there are two derivatives. Now, they're in separate equations. I could put them in the same equation. For example, I could take this equation, I could combine these two equations, then you'll see it's a second-order equation. So this is really an aside. But if I take this equation and I take the derivative of it, d squared CA2 prime dt squared. If I take the second derivative of this, then what do I get? I get 1 over tau 2 times dCA1 prime dt minus dCA2 prime dt minus k dCA2 prime dt. So all I did is I took the derivative of this equation. Now, because I know dCA1 prime dt, dCA1 prime dt, this thing is just 1 over tau 1 CA in prime minus CA1 prime. And this is minus dCA2 prime dt. And this is minus k dCA2 prime dt. So what you can see here immediately is I can combine these two equations to get a second order equation in CA2 prime where I've eliminated CA1 prime. Why did I bother doing that? I bothered doing that because I wanted to illustrate to you that when I have a quadratic here, when I have a quadratic in S, that means there are two derivatives. Either two derivatives in two equations that are linked,
for the very last line that you just wrote, are you ignoring the minus KCA?
why am I ignoring it? It's right here.
Okay.
So what I wanted to do is I wanted to illustrate here that when I have a quadratic here in S, that means it came from two derivatives. Either two derivatives in separate equations, or I could have combined them into a single equation that's a second order differential equation that gives me the same characteristic polynomial on the left. So that's just a little aside to verify that when I see a polynomial as the characteristic polynomial, if I look at the order of that polynomial, that should correspond to the number of derivatives, because each derivative gives me a power of S. Any questions on that so far? Okay, let's do one more example, and then we'll start getting a bit more general. One thing I'm going to refer to is this thing right here, which are the solutions to this problem, either when T1 and T2 are different or they're the same. And what we noted, just for fun, is if we looked at the S equation right before that, we looked at this equation, we solve for CA2 prime tilde. That means we divide by the characteristic polynomial. If we do that, multiply by S and take the limit as S goes to 0, this becomes 1. Multiply by S, that cancels out. Then I get CA2 prime tilde over CA in prime, and that just gives me KP2. Similarly, when I do the same thing here, I let it multiply by S, that cancels. I let S go to 0. Then I have CA1 prime tilde of 0 over CA in prime is just KP1. So somehow multiplying by S and letting S go to 0 tells me something about the steady state. It looks that way from these examples, but we really need to prove that. Let's do one more example before we start getting general. And that's the other canonical example we've been doing, where we have a tank with some inlet and an outlet. And I have the inlet volumetric flow rate V in, and here I have V out. And here I have the level, L of T. And if you remember, we said that V out we said equal to K times the square root of L. And we assume that for T less than 0, system is at steady state. And that V in goes through a step change at 0. So that was the problem that we've done in the past. And let's just remind ourselves the setup, and then we'll do it by Laplace transform. So if you remember, we have the cross-sectional area times dL dt, where this is the cross-sectional area, is equal to V in minus V out. V in minus K root L. And we said if we, in order to, we would linearize this. If we linearize, then we get V in minus K over 2 root L 0, L of 0, times L prime. So that's a rerun of what we've done before. I haven't bothered rederiving it. Okay, so we could, so this is the linearized T greater than 0. And then this one was exact. And of course I left something out. I left out minus the square root, minus K the square root of L0. So linearization was the value at 0 minus plus that change. And now if we take the exact for T equals 0, well, that was at steady state, but it was A dL of 0 dt, which happened to be 0 by hypothesis. It's at steady state. And that is equal to V in, and this is T greater than 0, and this is T less than 0, minus K root L0. So that's the exact for T equal to 0. So we should actually just say T equals 0. And when we took the difference here, remember this is the standard way of doing these problems. You start with the exact dynamic equation, you linearize it, the linearized dynamic, you subtract off the exact steady state equation, or T equals 0 equation, and then I get A dL prime dt is equal to, well, this just becomes V in prime. These two cancel because they're the same, and then I have minus K over 2 root L of 0 times L prime. And notice all I have are prime variables here. And I'm going to divide through by A, just so I can save, since I don't have a lot of blackboard space, I can save myself rewriting the same equation again. So this is the this is the dynamic equation that we need to solve. And what we did in the previous problem, what we did earlier, is, well, we moved this to the other side of the equation. So we have dL prime dt plus K over 2A root L of 0, L prime, is equal to V in prime over A. Notice, this is again of the exact same form that we spoke about. Sorry about that. Here we have the forcing function, and here we have the system. forcing, because V in prime is what's causing the change, and here with the reaction of the system. Okay, so what we did last time is we tried to we used the method of ordinary differential equations to solve this. By the way, we can call this thing, as we did previously, 1 over t, 1 over the time constant, because it has to have units of 1 over t, because this is L length units over time, so this has to be length units over time. And this is the time scale of which the system responds. So we can use the method of ordinary differential equations to solve it, or we can use Laplace transforms. So let's use Laplace transforms. If we Laplace transform, we have S L prime, we have L prime tilde times S, because we use this of a derivative. Again, since we're in prime variables, L prime of 0 is 0. And then I have plus 1 over t for this. And that's equal to V in prime, well, V in prime tilde, since V in prime is a step function, the Laplace transform of the step function is just 1 over s. So it's V in prime times 1 over s divided by a. So that comes along for the ride. And so this is 1 plus st over t times L prime tilde is equal to V in prime over SA. And again, let's notice I had one derivative here, so I have a linear equation here. Now I can bring all this to the other side of the equation. I have L prime tilde is V in prime over A times T divided by S1 plus ST. Now notice I have an S and a 1 plus ST here. The 1 plus ST comes from the system, it's the characteristic polynomial. The 1 over S comes from the forcing function, because Vn was a step function. So this came from the forcing function, this is the characteristic polynomial. And now I can invert this, L prime of t. Well, the constants come along for the ride, t over a, V in prime. And what line in the table, everyone has their table, you're supposed to bring it with you, always. What line in the table do I have a 1 over s, 1 over 1 plus st? Line 5 for a equals 0. So in line 5 for a equals 0, I just get 1 minus e to the minus ot over dt. So I got that right away. And what is that? We can plot that. So here I have t versus L prime, and here it was 0, and here what I get is a 1 minus an exponential, where this new value is what happens as t goes to infinity. As t goes to infinity, this becomes 0, so this new value is this. That's that new value. Now, one nice thing about this is we know that the Laplace transform of a theta function, of a step function, is 1 over s. We also know that the Laplace transform of delta t is equal to 1. So let's say instead of a step function, we had a different case where V in versus t, 0, was a certain value, and then we dumped a bucket of fluid in, and then it went back to where it was. So we dumped a bucket of fluid with m liters. We took a bucket and we dumped it in with m liters. So we can approximate this as m times a delta. So m times a delta, if I did this problem instead of this problem, then the only thing that would change is the Laplace transform of V in. This is the only thing that would change. So let's go back to here. I have L prime times s plus 1 over t is equal to a times 1 over a times the Laplace transform of V in prime. But V in prime is m delta t. So I just get m times 1. because the Laplace transform of delta t is 1. So shifting from one problem to another is really easy, because the whole thing that's changing is the forcing function. So now I have L prime, and this is tilde. L prime tilde is equal to m over a times, so mt over a over 1 plus st. So I just combine s plus 1 over t into 1 plus st over t. And that tells me, so now I have a 1, I don't have an s down here, I just have a 1 over 1 plus st. By the way, notice the left-hand side hasn't changed. It's only the forcing function that changed. What line in the table just has a 1 over 1 plus st? You want to get used to looking at this table. Line 4. Line 4 just has a 1 over 1 plus st. So notice what I have here is L prime of t then becomes 1 over, let's see, it was L prime tilde s, so L of t, 1 over tau, which is t, 1 over t, times e to the minus t over t, times the constants, where the constants is tm over a. So the t cancels. One outside, there's still a t in here. So what does this say? And I think there was a minus, it was e to the minus, right? Yes, e to the minus. So in this case, when we have L prime versus t, it was down here, and then L prime at t is equal to 0 was a certain value. But after that, it decays exponentially, back down to where it was, back down to 0. So what happens is the long-term solution here, this L prime goes to 0, because as t goes to infinity, the exponential goes to 0. And that makes sense. In the step change, in this particular case, the disturbance continues forever. So L prime adjusts to the new situation. We adjust, we have global warming. We're adjusting to the new temperatures, where we get a flood in our room. However, if it were just a step change, if we only had one rainstorm and not a rainstorm every week, then okay, 3 or 4 is out of action today, but next week it will be fixed and we'll be back where we were. So that because it's a one-time event as opposed to something that's continued. Now, again, let's notice what's Kp. Kp is L prime of 0. I'm sorry, it's the L prime of 0 over the over V in prime. Well, we know that it's going to be 0 because L prime of infinity, I'm sorry, L prime of infinity. L prime of infinity is 0. So Kp here is 0 because it's L prime of infinity over V in prime. Well, L prime of infinity is 0 because it goes down to 0 here. And again, let's see if our trick, what we did before, multiply by s and say, and take the limit as s goes to 0 will work. Well, if we take this guy and we multiply by s, we have an s in the numerator and a 1 plus s in the denominator. We take the limit as s goes to 0, this goes to 1, but the numerator goes to 0 because there's an s sitting here. So I get the right answer again. And the question is that a, are we lucky there, or is there something to that, something more general than that? First, are there any questions? Well, I have a question, where's the rest of the class? We only have 10 people, it's half the class. Well, you can't answer that because you're here. We do have a problem with attendance. I can't believe that every class there's a problem getting here. If people are having trouble getting here every class, then they need to leave home earlier. In any case. So let's go back to some we'll toss around. Actually, and one of the 10 people here is the TA. So 2, 4, 8, 9. 9 out of 19 is less than 50%. Okay, so including the person who's usually supposed to be re-recording this, as opposed to Chris. who is nice enough to record. I hope you can listen while you're recording.
No.
No?
No. It's like watching TV, your brain tunes out.
Oh, that's no good.
No, it's not.
So concentrate less on the recording and more on what we're doing.
I'll try.
Okay, so the first thing is, let's just notice, if you remember, one example I gave early in the semester, we're going to use this, it looks like I'm going a little off track here. One example I gave early in the semester is when you're in the shower. When you're in the shower, then, and the water is too hot, then you turn the hot water down. But in most buildings, the reaction is not instantaneous. It takes a while for it to get colder. So you better not react too fast, because then it's not going to converge. Then it's going to get too cold, then too hot, then too cold. So we need to know how to deal with delays. And so even though we're not going to do a problem with delays yet, we were doing some of the basics of the Laplace transform. So I'm going to do the Laplace transform of the delay. So if we have a function f of t minus theta, that's a theta second delay. So if something, so that's what I mean by a delay of theta seconds. When I say seconds, that's because I happen to be thinking in units of seconds. If I have a problem that responds in hours, then it's hours, or days, or weeks, whatever it is, whatever your time units are. So what's the Laplace transform of this? So f of t minus theta tilde is the integral from 0 to infinity, e to the minus st, f of t minus theta, dt. Well, in order to, this is an f, I want to make it not look like a t. So let's let this be, say, u, it'll be t minus theta, and I'm going to change variables. So I'm going to let u be t minus theta. So du is dt, because theta is a constant. And I can rewrite this as the integral of, now, remember, t now is theta plus u. So it's e to the minus su, e to the minus s theta. Because it's s, e to the minus s theta plus u, but theta is a constant, so I can pull it out of the integral. Times f of u du. And when t is 0, u is 0 is minus theta. But f is presumed to be 0 when its argument is less than 0. So even though this is t minus theta, and of course infinity minus theta is still infinity, since f is 0 for u less than 0, I can just replace this with 0. I'm sorry, this is 0 minus theta, which is 0. In which case, this is e to the minus s theta times f tilde of s. So we know that f of t minus theta tilde is e to the minus s theta f tilde of s. So as opposed to derivatives that or integrals that give me an s in the numerator and an s in the denominator, a delay gives me an exponential. So when I see exponentials, I think of delays. Now, notice this says f of t minus theta. We're thinking of something that depends on something that happened in the past. So there's a delay. I turn the hot water down, and a few seconds later, I see the result. We said in physics there's the notion of causality, which means things can only depend on what's happening now or what happened in the past. It can't depend on what's going to happen tomorrow. What happens now can't depend on what's going to happen tomorrow. So how you do on a test today depends on how much you studied in the past, not on how much you're going to study next week. So that means it's only sensible to have an exponential with a negative sign. If I had an exponential with a plus sign, that would correspond to a negative theta. That would be t plus theta. That would correspond to the effect now being caused by something theta seconds in the future. So that's obviously not that's something by causality we're not going to allow. Not physical. Okay, that's an aside. Now let's get back to what we were doing here. And what we're doing here depends on what we call, the first thing we want is the, what's the theorem called? The long time theorem? There's a name for it. Final value theorem. And the final value theorem says the limit as t goes to infinity of f of t is equal to the limit as s goes to 0 of s f of s. And is there an f of 0 in there? I don't think so. No. So, in other words, exactly what we were doing in all these examples was not an accident, but it's actually true. So let's prove it. You know, just like in a math class, where we sometimes prove things. This one's actually quite easy. So, we know that f tilde, the f dt integral from 0 to infinity of e to the minus st dt. So this is f tilde of s. Let's take the limit as s goes to 0 of this. Or do I want to do, well, let's look, this is the Laplace transform of the derivative. And we know that this is equal to s f tilde of s minus f of 0. So this is exactly just what I wrote here. And now let's take the limit as s goes to 0 of both sides of the equation. So let's take the limit as s goes to 0 of both sides of the equation. Yeah, so let's do it. If I take the limit as s goes to 0 to the left-hand side, when s goes to 0, this thing goes to 1. So I have the integral from 0 to infinity, df dt times 1 dt. So again, here I'm cheating. I'm taking the limit of an integral, the integral itself is a limit, and I'm switching the order of the limits. And there is a series of theorems, if you ever take an advanced calculus class, called Fubini theorems, F-U-B-I-N-I, which tells you exactly when you're allowed to switch limits and when you're not. And the basic idea is you're allowed to switch limits if both answers are finite, then they're going to be the same. So if they're both answers are finite, then you're allowed to switch limits. That's the shorthand of it. And what do I get here when I do this? Well, this thing is just the integral of the derivative, which means it's f of infinity minus f of 0. I just take f at the top and minus f at the bottom. And that's equal to the limit as s goes to 0 of s f tilde of s minus f of 0. So what you can see here is the f of 0 cancels, and I have the limit as t goes to infinity. And I should actually just write this. Because we don't know that there is a limit. If there is a limit of f of t is equal to the limit as s goes to 0 of s f tilde of s, which is exactly what we set out to prove. So that says what we did here by multiplying by s and taking the limit as s goes to 0 has to, by virtue of the final value theorem, give me the final value. Give me the limit as t goes to infinity of f of t. Well, then there's also the initial value theorem. Bless you. The initial value theorem says the limit as s goes to infinity. Now, if you remember, we said that there was a certain duality between t and s. What this says is when t goes to infinity, when s goes to 0, it tells you something about t goes to infinity. And the duality would, that is that f tilde of s and f of t were somehow dual, that is, partners, opposites. Well then, maybe if I take s goes to infinity, that should tell me something about t goes to 0. And in fact, that's true. The limit as s goes to infinity of f tilde of s is equal to the limit as t goes to 0 of f of t. prove that. Yeah.
I think you're missing a tilde for the
I'm
bottom
missing what?
one. The one on the bottom is not corresponding to the one at
To the top. Here's
the top. Oh,
the-
sorry, like
How about counting one?
this isn't the tilde is not.
I left the tilde in here. Thank you. Okay, thank you. Yeah, I left out the tilde. Where f tilde is always a function of s, and f is always a function of t. Okay, so again, let's look at this, and let's look at the case. So here I have, and I may have lost an s here. We'll see in a second. Again, let's look at the limit now as s goes to infinity of the integral from 0 to infinity, df dt, e to the minus st dt is equal to s f tilde of s minus f of 0. Well, as s goes to infinity, this just goes to 0. So the integral of 0 is just 0, and I have 0 is at the limit as s goes to infinity of s f tilde of s minus f of 0, which tells me this, that the limit as s goes to infinity of s f tilde of s is equal to f of 0. So did we prove this as well? So these are really useful things, because if I didn't know the initial condition, this tells me, or this is a way of checking that I get the initial condition right. When I take the limit as s goes to infinity, I should get the initial condition back. Here I should get the infinite time value, which is either steady or not steady. For example, there may not be a limit, it may go to infinity. I'll find that out here, and that will tell me there is no steady state. Now, there's a hypothesis I left out here, and the hypothesis is, suppose f of t, or f of s, tilde of s, is continuous from 0 to infinity. So I need that as a hypothesis. It has to be continuous. If it's not continuous, then I claim I can violate this. Let me give you an example of that. So an example is where f tilde of s is not continuous. So let's let f tilde of s be equal to k times, make sure I get this right, 1 over s, st minus 1. Now recall, we always had in our denominator 1 plus st. So notice that as long as, in order for s to be 0, for example, then when s is 0, as long for this to be 0 in the denominator, make this thing blow up, I would need s as minus 1 over t. All I care about it being continuous is between 0 to infinity, so there's no problem here. I never have a 0 in the denominator here for t positive. But when I come over here, because I put a negative here, when s is 1 over t, then the denominator has a 0 in it and it blows up. If it blows up, then it's no longer continuous. And why is that a problem? Because if you actually look at the inversion formula, which I didn't write down, it involves an integral of f tilde. And the integral of f tilde won't exist if f tilde is infinite somewhere. If it blows up, it's likely not to exist. So let's notice that if I invert this, just do the direct inversion. So again, this is from line 5. From line 5, I keep the k, line 5. And so this is, so I can note that this is equal to minus k over s, 1 minus st. So when I invert it, I get minus k. And in line 5, again for a is equal to 0, I have a 1 plus, or 1 minus. And now I have e to the minus t over t. E to the minus little t over big T. But here, because I have a minus sign here, in the example, I had a plus. So that says I have a minus t here. So this is over minus t. The minuses cancel, and I get 1 plus e to the t over t. And let's notice what happens as t goes to infinity. The true solution as t goes to infinity, well, it's what happens to the e to the t, little t over big T as t goes to infinity? Higher mathematics? What's the e to the t as t goes to infinity? This is really, what is e to the t as t goes to infinity?
It's infinity.
Infinity. If you're having a problem with what e to the x is as x goes to infinity, then we're in trouble. Okay, so this is infinity. So infinity, and there was a minus sign here? Okay, so if this is infinity, I have a minus infinity times a minus k is plus infinity. So this whole thing goes to infinity. On the other hand, if I multiply by s, if I take the limit as s goes to 0 of s times minus k over s1 minus st, the s's cancel, and I get, when s goes to 0, I just get minus k. So minus k and infinity are not the same. They're different. Obviously, minus k is not infinity. And in fact, what this is telling me, because one answer is infinite and the other one is finite, is that it was not legal to change the limits, because one answer gives me infinity and the other one gives me finite value, which is what the Fubini theorems tell me. It's legal to switch it's legitimate to switch the limits if both answers are finite. Then you're guaranteed that they'll be the same. But if one of them is finite, one of them is infinite, they're obviously not the same. Any questions on that? Questions? Okay, so our goal, now, of course, this table only has 18 lines. And chances are there are more than 18 answers I'm going to get when I do lots of different problems for f tilde of s. So, what do I do? I mean, there are tables that are like 5 pages instead of 1 page, but they're still never going to be complete. And you try to make the tables as brief as possible and as uncomplicated as possible. So you can imagine I can take the 18 guys on the right and do various linear combinations of them. I could do an infinite number of linear combinations, and each one's going to give me some complicated form. And I can't list an infinite number of them, and there's no reason to. Whenever I have a complicated form, I want to simplify it into its simplest forms and work from there. So what you do, and you hopefully have seen this, at least the simplest version of this in reaction engineering, and it's called partial fractions decomposition. And what is that? Well, let's look at the following problem. 1 over s minus a, s minus b. I don't want to write it as a product. I want to write it as something simple, just a over s minus a plus b over s minus b. Did you do this in reaction engineering? Usually it's done like the second week of reaction engineering. Yes, I see one head nodding yes, so that means it happened, and maybe the other people didn't pay attention, or they just don't like to nod their head. Okay, so how do you solve this? We're going to do it more generally, but I just want to illustrate this. And so if I have a problem like this, I break it up into the sum of 2 easier ones. That's the idea here. So in order to solve, I need to figure out what a and b are. So the way I solve for it, in the simplest case, is I multiply it by s minus a, s minus b. And I get 1 is equal to a times s minus b. Because when I multiply by s minus a, s minus b, the denominator cancel. Here s minus a cancels, I'm left with s minus b. And here I get b times s minus a. And if this is going to be true, not just for one s, but for all s's, I want this true for all s's. If it were true for one s, I couldn't do this. But if I want it to be true for all s's, I take the coefficient of s to the 0 on both sides of the equation has to be the same, and the coefficient of s to the first on both sides of the equation has to be the same. And if I had a quadratic, it would be s to the second as well. So on the left, I have a 1 times s to the 0, and on the right, I've got minus a, I've got minus ba minus ab. On the other hand, for s to the first, I have no s's on the right, on the left, but on the right, I have a plus b. So immediately, this tells me that b is equal to minus a, and this thing has an a times a minus b, because b has become minus a. So I've got a plus AA, and I've got a minus AB. So this tells me, if this is equal to 1, that A is 1 over A minus B, and B is equal to minus A. So that tells me that 1 over S minus A, S minus B, is equal to 1 over A minus B times 1 over S minus A minus 1 over S minus B. So it was just a little bit of algebra here, but the point here was we wanted to break up something that was a 1 over product into two terms, 1 over S minus A and another term with an S minus B, because this is easier. And chances are this I'll find in the table, but this one I might not find in the table. This particular table I happen to find this also, but I'm just illustrating something. And we needed to solve for the coefficients, so we found the coefficients. So this is the nature of the problem, of what we're trying to do clear. Okay, so how do we do this more generally? Well, more generally, I have, and I'm not going to do the most general, but let's assume that I have a function. What do I want to call it? Let's just call it n tilde of s over d tilde of s. N is numerator, d is denominator, where n tilde of s and d tilde of s are assumed to be polynomials. I'm going to assume that they're polynomials. That's because that's what we seem to be coming across most of the time. And what I would like, so there are going to be three cases. Case one is where the roots, so S is a polynomial, it has roots. The roots of d tilde of S are distinct and real. So you never have the same root twice. You don't have an S minus A squared. Case two is where you have multiple roots. So this is the case, say, S minus S1, S minus S2, dot, 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 S minus Sn, where S1 through Sn are all different. Multiple roots is where I have an S minus S1 to a power that's different from 1, say, cubed in d tilde. And case 3 is where I have S1 and S2 are complex conjugates. i.e., S1 is alpha plus I omega, and S2 is alpha minus I omega. Now, why would I have complex conjugates? This is something that I'm not going to prove for you. This is something that you might prove in a analysis class, but it's intuitively appealing. Is that if I have a polynomial where the coefficients are all real, so like a polynomial, say quadratic or cubic, where the coefficients are all real, then if I have one complex root, I need its complex conjugate, because otherwise when I multiply all these guys out, I would get complex coefficients. The only way for the coefficient, for none of the coefficients to be complex, is if whenever I have a complex number, I have its complex conjugate. So if you think of, for example, the quadratic formula, minus b plus or minus the square root of something over 2a. If that square root is the square root of a negative number, then you get minus b plus or minus that square root, plus or minus I times something. Those are complex conjugates. So that's an example. The quadratic formula is a direct illustration of that fact. Okay, so there are, and now of course I can get more complicated than this, but for example, I can combine case 2 and case 3, where I have this thing squared and this thing, 2 of these and 2 of these. But that's sort of a trivial extension. So what I'm going to do now, I obviously won't get through all of them today, because I only have like 15 minutes or so, but I can certainly do the first one. So let's do case 1. Okay, if we do case 1, then so for case 1, I'm going to assume, I'm going to write n tilde, so case 1 says d tilde of s is equal to s minus s1, s minus s2, s minus sn, all s is different, s1, s2, sn, all different. Okay, so then I could write d tilde of s as s minus s1 times, say, r tilde of s. So I'm going to pick out the first factor and lump all the rest in r tilde. Then what do I do here? Then I could write that n tilde of s over d tilde of s is equal to n tilde of s divided by r tilde of s over s minus s1. And by hypothesis, n is a polynomial, so when s is s1, it can't blow up. And by hypothesis, r tilde of s1 is non-zero, because if it were 0, then I would have a multiple root. So by hypothesis, n tilde of s1 or r tilde of s1 is finite. And generally, we say that we cancel, we usually say that we cancel like factors. So it's not only finite, but it's non-zero. Because we've canceled like factors in n tilde and d tilde. So there's no s minus s1 in n tilde, because otherwise we would have canceled it already. And this thing I can call, say, m tilde of s. And I claim this can be written as a c1 over s minus s1 plus some remainder r tilde of s. This c1 is playing the role exactly of a, what a was here. It was a over s minus a plus the rest. So this a now I'm doing it more generally, I'm calling it c1. Of course, you know, when you take an a and you turn it into a c, that's more general, right? That was a joke. Okay. So let's see where that comes from. And moreover, I claim that c1 is equal to m tilde of s1. Just m tilde of s1. Okay, so let's see where that comes from. All right, so let's multiply, let's take this equation. And let's call this equation star. So, prove. Let's take star and multiply by s minus s1. And then we'll take the limit as s goes to s1. So if I multiply by s minus s1, I have n tilde of s 1 over d tilde of S1 times S minus S1 times S1 minus S1, so I multiply by this, is equal to C1, I multiply by S minus S1, plus R tilde of S1 times S minus S1, S1 minus S1. And that's from here is equal to M tilde of S1. M tilde of S1, because when I multiply by S minus S1, they cancel. So what's left? S minus S1 is 0. This by hypothesis is finite. Well, actually, no, it's not 0. Let's go back. D tilde of S, D tilde is S minus S1 times S minus S2, dot, 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 S minus Sn. So this cancels. And notice here I have, here R tilde of S, since there are no more S minus S1s in the denominator of R tilde, because there are no more S minus S1s here, this is 0. So immediately I have N tilde of S1 is equal to C1. So we prove that. And let's look at an example before we go any further. So we figured out that if I have N tilde over D tilde, I just have to calculate N tilde, and I get C1 by taking M tilde of S1. So let's look at an example. And let's look at, say, S plus 3 over S minus 1, S minus 2. Is that the example I want to do? S minus 2. So that's an example. And I claim, so let's see what that is. So this is, so N tilde, this is N tilde. This is D tilde. And R tilde is equal to S minus S. Well, so let's write this as C1 over S minus 1. So let's make this S1. In which case, R tilde is S minus 2. And I have R tilde of S. So I claim in order to get C1, all I have to do is take M tilde of S1. So M tilde, what's M tilde? M tilde is N tilde of S over R tilde of S. So N tilde is S plus 3, and R tilde is S minus 2. And now if I take M tilde of S1, of 1, so I get 4 over 1 minus 2, which is minus 4. So I claim that C1 is minus 4. Well, let's calculate R tilde of S. If I've done this right, then R tilde of S won't have any S minus 1s in its denominator. So let's see. So I've got S plus, so let's find R tilde of S. So if I have S plus 3, R tilde of S is equal to this guy minus this guy. So it's S plus 3 over S minus 1, S minus 2, minus R tilde. I'm sorry, minus this guy. Minus a minus is a plus over S minus 1. Is that clear what I'm doing? I'm solving for R tilde. And if I get R tilde right, there should be no S minus 1 in the denominator. So I factor out an S minus 1 in the denominator. And I have S plus 3 over S minus 2 plus 4 in the numerator. So I've got a 1 over S minus 1. And now to bring this together, I have a 4S. I have S plus 3 plus 4 times 4S minus 8 over S minus 2. So I just brought it under 1 factor. So this is equal to S plus 4S is 5S. 3 minus 8 is minus 5 over S minus 2, S minus 1. This is 5 times S minus 1 over s minus 2, s minus 1, which is 5 over s minus 2. So that means I did it right. That means this worked because r tilde doesn't have an s minus 1 in the denominator. If I had done it wrong, gotten the wrong answer, there'd still be an s minus 1 in the denominator. So what we find here, we've already done it, is therefore s plus 3 over s minus 1, s minus 2 is equal to minus 4 over s minus 1 plus 5 over s minus 2. Now, if I had something more than a quadratic, let's say I had 5 factors in the denominator and not 2, then the remainder would be a quartic instead of a quintic. So this is, if I started out with 5 factors here, I take out 1, the remainder would have 4. And then I would do the same thing to the remainder. I would do the same thing I did here, the exact same procedure, and I would turn the quartic into a single term plus a cubic, and I keep going until I'm done. Any questions on that? Okay, so let's notice, let's do an example. Another example. Well, let's notice something. The thing I want to notice is I can also write this. C tilde C1 can also be written as n tilde of S1 over dd tilde ds at S is equal to S1. Now, where did that come from? How do I know that? Well, let's notice something. If d tilde, well, I already had it. So here's d tilde. For this value, where did I write it? Now I'll write it again. So if d tilde of s is s minus s1, s minus s2, dot 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 s minus sn, d tilde ds, d tilde ds is equal to, well, the derivative of the first factor times all the rest. So it's s minus s2, dot 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 s minus sn, plus s minus s1 times s minus s3, dot 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 s minus sn, plus s minus s1 times s minus s2 times s minus s4, dot 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 s minus sn, that plus dot 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 s minus s1, dot 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 s minus sn minus 1. So how did I get that? When I have got, remember, the product rule says I take the derivative of the first factor times all the rest, plus the derivative of the second factor times all the rest, etc. And notice that except for the first term, all the other factors have an s minus s1 in them. They all have an s minus s1 in them. So when I take the limit as s1 goes to 0, all these other factors are 0 because they all have an s minus s1, and this one doesn't. And this guy is exactly what we called r tilde of s. This is exactly what we called r tilde of s. It's all the factors except for s minus s1. So what we have is that r tilde of s is equal to dd tilde ds at s1. R tilde of s1, it's not in, r tilde of s1 is dd tilde ds at s1. It wouldn't be anywhere else, because anywhere else I have all the other terms. But at S1, they happen to agree. And that's actually quite useful. Why is that useful? Well, is there an example I can give? Yeah. Let's say, and this sort of violates our assumptions, but let's say n tilde were signed. be sine of s. Well, then, what's r tilde? R tilde of s would be sine of s over s minus s1. That's kind of a, because r tilde times s minus s1 has to give me d tilde. It should be d tilde. So obviously, I don't want to deal with r tilde of s, because that's a mess. But let's say I want to know the value at 0. So if I want to know the value at 0, m tilde at 0, that's equal to the numerator at 0, n tilde of 0, divided by the derivative. I just have to take the derivative. What's the derivative of sine?
Cosine.
Cosine. And the cosine of 0 is 1. So if I have something like the sine, this formula is really useful because it gives me the answer without having to deal with this guy. I could deal with that, but then I have to start taking limits. That particular function is easy to take the limit of, but other functions may not be that easy to take a limit of. Now, what's the point of all this? What's the point of taking something like this, or a product of factors, and breaking them up? Well, if I had a little more board space, I can do it. I will create board space. New board space. So, if I have a bunch of terms, now the solution, now when I'm done with this, I have a bunch of terms of CI over S minus SI. I have a bunch of terms that look like that. Because each term looks like a constant over S minus SI. Well, if this is f of s, f tilde of s, then I can immediately write f of t, because this is going to be a sum of terms on I, ci. And what happens with 1 over s minus si? Well, if I look on the table, if you look at line 4 of the table is 1 over 1 plus s tau. What does line 4 tell me? Well, I can write it as of this form. I can write this as 1 over tau times s plus 1 over tau. And I could make this a minus, and this is a minus a minus. So 1 over 1 plus s tau is minus 1 over tau over s minus 1 over minus tau. So now I can look back at the table. In line 4 is 1 over 1, I'm sorry, this is a plus. Did I get that right?
Yeah.
Okay. So this tells me in the table that SI is just, this is just SI. So what does this tell me? This says I have a 1 over tau, the minus, and 1 over 1 plus s tau. So what's the inverse here? The inverse is 1 over tau. 1 over tau is, again, a minus tau, times e to the minus t over tau. E to the minus t divided by this guy. Divided by this gives me a plus t tau. I'm sorry. Why don't we go back and read it more carefully? So I've got a CI over minus tau. And let's notice that minus 1 over tau is exactly SI. So this is just SI. And now I need an exponential. The exponential is e to the minus t over tau. Minus 1 over tau is just SI, so it's e to the minus SI t, e to the SI t. So if I haven't made a mistake there, that's the minus 1 over tau, and I have another minus 1 over tau in the denominator. So I get f of t is just, when I go backwards, f of t is just the sum of ci's times exponentials. So by breaking up something like this into terms that look like this, the inverse is easy. It's all line 4, and it's e to the SIT. And what does e to the SIT tell me? If SI is negative, then I'm lucky. Then all the exponentials decay. But if even one of the SIs is positive, no steady state for you, no steady state land, it goes to infinity. That's really bad, but I need to know that. I can't just throw away the DDT term. So knowing the roots of the denominator are really important. They determine what's in the exponent. Isn't it curious how the roots of the numerator don't have anything to do with the stability? They don't. They affect the coefficients. The numerator affects the coefficients. The denominator, its roots, affect the stability of the system. Do you go to infinity? Do you go to 0? And it's going to get even more interesting when I can have complex numbers. Because again, spoiler alert, when you have complex exponents, that's going to be directly related to sines and cosines, which we're going to do next time. Questions? Moses, what's the situation on homeworks?
6 people submitted the last 2 months.
When will they get them back?
I've met up to 3 homeworks already. I just need them back.
Okay, well, so we'll have the exam next Monday. Hopefully we'll be back in our normal room because it's too small a room to have an exam in because people are on top of each other. And I will send a slightly unfriendly email saying people have to come to class.
The content will still be the same, right?
Yes, yes. Content will be the same.